Let's dive into something known as the Lewis structures, and these represent the valence electrons of an atom. So for example, carbon has 4 valence electrons, and that can be represented by 4 dots. Oxygen has 6 valence electrons, and thus can be represented by 6 dots. There's no particular order in which making the dots, but I like to do it counterclockwise. Boron has 4 valence electrons, so 4 dots, and beryllium has 2 valence electrons, and thus 2 dots. These dot structures can help us understand bonding. So if we have lithium is a cation, and it wants to lose 1 valence electron, and chlorine is an anion. It has 7 valence electrons, and it wants to gain 1. So lithium is a cation, it's a metal, and chlorine is a non-metal, and it's a negative charge since it wants to gain 1. So lithium can transfer its valence electron over here, making chlorine have a full outer shell, and lithium is also stable. This satisfies the octet for both lithium and chlorine, making it lithium chloride. This can also be true for sodium chloride, also known as table salt. Since sodium is a +1 charge, wants to lose 1, chlorine has a -1 charge, wants to gain 1. So opposite equal charges attract, and this becomes sodium chloride. Here's the Lewis structure for that. So sodium, 1 valence electron, chlorine, 7, transfers 1, it becomes sodium chloride. That was ionic bonding, and it can also explain covalent bonding. So here's oxygen again. Oxygen, 4, 5, 6 valence electrons. And there's another oxygen, 1, 2, 3, 4, 5, 6 valence electrons. By the way, ionic bonding is when they transfer valence electrons, and covalent bonding is when they share them. So these oxygens, they both need to gain 2 valence electrons to satisfy the octet rule. So they can share these valence electrons. And now this oxygen can act like it has 8, which satisfies it and making it stable. And this oxygen also can act like it has 8, making it stable as well. This creates the diatomic particle O2, known as oxygen gas. We can also determine how many bonds, such as O2, had double covalent bonds, as this. We can determine how many bonds other elements have, like carbon, beryllium, and let's say boron. Carbon has 4 valence electrons, and it needs to gain 4 more or lose 4 more, and since it's a nonmetal, it technically needs to lose 4 more. 4 valence electrons. So it can form 4 covalent bonds. Beryllium has 2 valence electrons, and it needs to lose 2, so it can form 2 bonds. Boron has 4 valence electrons, and thus it can also have 4 covalent bonds. Alright, let's try a couple of examples together. So here is potassium, sodium, nitrogen, and fluorine. Potassium has 1 valence electron. Sodium also has 1 valence electron. Nitrogen has 5 valence electrons, and fluorine has 7. It is the most reactive out of all of them, and a halogen. So let's determine how many bonds these atoms would make. So since it needs to lose 1, it would make 1 bond. Since it also needs to lose 1, it would make 1 bond. Since this nitrogen wants to gain 3, it would make 3 bonds. And since fluorine wants to gain 1, it would make 1 bond. Okay, now let's try forming some Lewis structures. Let's form the Lewis structure of nitrogen oxide. Forming a covalent bond. So nitrogen 5, 4, 5, oxygen 6, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So these two oxygens need to gain 4 in total, and nitrogen needs to gain 3 in total. So is this possible? Under rare circumstances, but in this case, no. It is not possible. It was a trick question. Okay, that's just something that is actually possible though. By the way, I also have to clarify, nitrogen dioxide can form, but it doesn't follow the standard octet rule. That's why we're not following it right now. But something that is a little more common is H2O, or water. So hydrogen, another hydrogen, and here is an oxygen 4, 5, 6. So this can form a covalent bond, and I wrote it the wrong way, but this also forms a covalent bond. So it forms 2 bonds, but it does satisfy the octet rule since hydrogen is happy with 2, the other hydrogen is happy with 2, and the oxygen is happy with 8.